The universe is not static. It never has been. But for most of human history, that's exactly what we believed. Look up at the night sky. The stars don't seem to move. The constellations stay the same. Night after night, year after year, the moon glides smoothly. The planets wander a little, but always return. To ancient eyes, it all felt permanent, still, like a great cosmic painting hung above the world. So we built our understanding of the universe on that stillness. The Earth, we thought, must be the center, solid and unmoving. Everything else, the sun, the stars, the heavens, must be spinning around us. A perfect celestial dance, set in motion by something divine, but always repeating. For centuries, this view held, not because people lacked imagination, but because it worked. It matched what the eyes could see. It made sense of the seasons. It explained eclipses and alignments. It gave us comfort, a stable world beneath our feet, surrounded by orderly skies. Then came a crack in that illusion. First, Copernicus dared to suggest the Earth might not be the center, after all. Then, Galileo pointed a telescope at the heavens and saw moons circling Jupiter, proof that not everything orbited us. And then came Kepler, who studied the paths of planets and discovered they didn't move in perfect circles, but in ellipses, guided by invisible forces, following precise mathematical laws. Bit by bit, the stillness faded. Today, we know the truth is far stranger than anyone imagined. Space isn't silent and fixed, it's in motion everywhere. Not just planets and stars, but galaxies, clusters, and superclusters. Even the very fabric of space is on the move, stretching in all directions. And yet, we still feel like we're standing still. The ground doesn't shake, the stars don't blur past us. The universe feels calm. But that calm is just a trick of scale, a mirage. Because the truth is, even now, right this second, we're spinning on a planet, orbiting a star, flying through a galaxy, all while being pulled by a force we can't even see. The old picture of a still universe is gone. We've stepped into a story of hidden motion, and we're finally beginning to understand what that motion means. Chapter 1: The Journey of Our Planet. For millennia, the dominant view of the universe had placed Earth at its absolute center. After all, that was what people knew. During the day, they saw clouds glide above them and the sun shine brightly overhead. At night, they saw the moon and the stars stretched out like a giant cosmic painting. Every celestial object appeared to be in motion, and they believed they were at the center of it all. This view was found across the ancient world, from Chinese sky lore to Mayan cosmology. But it was in the Hellenic world that this idea not only became an accepted myth, it was structured into a technical cosmological model. And the man who did that was Claudius Ptolemy. Ptolemy lived in Alexandria around the 2nd century CE, during the height of Roman Egypt. He was a scholar, a mathematician, and more than anything, an astronomer who wanted to make sense of the skies, not just philosophically but with numbers. He inherited a rich tradition from Babylonian star catalogues, Egyptian astronomy, and Greek geometric modeling. But what he did with that knowledge was something monumental. He compiled, organized, and refined it into a systematic model of the cosmos, laid out in a massive work known as the Almagest. The work was so influential that it became the definitive guide to the universe for over 1,000 years. In Ptolemy's model, Earth sat at the very center of the universe, perfectly still, unmoving. Around it, in concentric spheres, revolved everything else: the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally, the sphere of fixed stars. Beyond that, nothing humans could know. The entire cosmos was a giant set of nested spheres, perfectly ordered, with Earth as the pivot of all celestial motion. Each celestial body was embedded in a transparent crystalline sphere that spun smoothly around us. The stars were affixed to the outermost shell, which rotated once every day, giving us night and day. This wasn't just a random guess. Ptolemy used observations to make his model mathematically functional. He believed the heavens must move in perfect circles because the circle was the most perfect shape in Greek philosophy. But that created a problem. When people tracked the planets over time, especially Mars, Jupiter, and Saturn, they noticed strange behavior. Sometimes a planet would slow down, stop, and even move backward in the sky before resuming its forward path. This retrograde motion made no sense if all the planets moved in simple circles around Earth. To fix that, Ptolemy introduced epicycles. These were small circular paths that each planet traveled while that entire smaller circle orbited Earth along a larger circle called the different. So a planet didn't just circle Earth, it circled a point that itself was circle an Earth. This looping motion could recreate the backward steps seen in the sky, but even that wasn't enough. The math didn't quite line up with what astronomers observed, so Ptolemy introduced another tweak. The equant. This was an imaginary point, slightly off-center from Earth. He claimed that if you measured the planet's motion from this equant point, the movement appeared uniform not from the actual center, but from this offset position. The model had been refined for centuries, polished and preserved. It had shaped calendars, timekeeping, astrology, and religious worldviews. It had served empires and guided scholars. It had explained the skies for over 1,000 years. But no amount of complexity could hide the truth forever. Observers were beginning to ask hard questions. A few began looking for a simpler explanation, and one name stood out. A name whose revolution still echoes to this day. It all began quietly in 1543, with the publication of a book that would shake the foundations of astronomy. Its title was De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. And its author wasn't some famous scientist or thinker. He was a priest. His name was Nicolaus Copernicus. That might sound odd today, but back then it made sense. The church was the epicenter of intellectual life in Europe. If you wanted to study mathematics, astronomy, or philosophy, the church was where you did it. Monasteries and cathedral schools were the libraries and laboratories of their time. Born in what is now Poland, Copernicus studied law and medicine, dabbled in economics, and became fluent in Greek and Latin. But his real passion was the sky. And for years he had been quietly collecting observations, running calculations, and writing out an idea that had been forming in his mind. One that went against everything he had been taught. His idea challenged the entire system people believed in. So he kept it mostly to himself. For decades he hesitated, knowing the risks, not just scientific criticism but religious and political backlash too. Near the end of his life, he finally published that idea reluctantly. In it he outlined a model of the universe where the sun, not the Earth, was at the center. The Earth, he said, was a planet just like Mars and Jupiter, and it orbited the sun once a year. But he didn't stop there. Based on his observation, Copernicus proposed 3 distinct motions of Earth. First, Earth rotates on its axis every 24 hours. That daily rotation is what makes the stars appear to rise and set across the sky. Second, Earth orbits the sun once per year. That revolution around the sun explains the changing positions of the planets and the seasons. And third, Earth wobbles slightly, tracing a small circle while it moves through its orbit, a motion we now associate with the tilt of Earth's axis and the phenomenon of precession. These ideas weren't just guesses. Copernicus spent decades developing complex geometric models and astronomical tables. He used trigonometry to calculate the relative distances of the planets from the sun. He ordered the planets based on how fast they appeared to move across the sky. The closer a planet was to the sun, the faster it orbited. That lined up beautifully with what he saw. But even though Copernicus's model made conceptual sense, it didn't improve accuracy. That's because he still assumed planets moved in perfect circles, just like Ptolemy. And that made his predictions only about as good as the old system, in some cases worse. Then came the telescope. It wasn't invented by a scientist. Actually, it started as a Dutch novelty, just a few lenses slapped together by spectacle makers. But when news of this strange device reached Italy, one man saw more than just novelty: Galileo Galilei. He didn't invent the telescope, but he turned it into a scientific instrument. In 1609, Galileo pointed it to the heavens, and what he saw would rattle the old order. First, he looked at the moon through the eyepiece. It wasn't the perfect, smooth, divine orb that the ancients had believed. It had craters, mountains, and shadows. It looked a lot like Earth. Then he looked at Jupiter, and there, dancing around the planet, were 4 small points of light. Night after night he tracked them, and they changed position, but always stayed near Jupiter. These were moons orbiting something other than Earth. This was a huge discovery because the geocentric model claimed that everything had to orbit Earth. But here was Jupiter stealing that spotlight with its own system of orbiting bodies. For years, Kepler tried to force the data into circular orbits. That's what everyone assumed. Circles were divine, perfect. The heavens had to move in circles. But Mars didn't care about philosophy. So finally, Kepler stopped forcing the math. He let the data speak, and what it said changed everything. Kepler discovered that planets don't move in perfect circles at all. They move in ellipses. That was his first law. All planets move around the Sun in elliptical orbits, with the Sun at one focus of the ellipse. This means that a planet's path isn't a perfect circle, but rather an oval shape. Kepler also noticed something else. Planets don't move at constant speeds. They sweep across space faster when they're closer to the Sun and slower when they're farther away. That's his second law. A line connecting a planet to the Sun sweeps out equal areas during equal intervals of time. In other words, as a planet moves along its elliptical orbit, the area it sweeps out in, say, a month, is always the same, whether it's near the Sun or far. This explained the strange speeds of planets, especially Mars. And then came the third law, the one that stitched the entire system together, also known as the law of periods. Kepler found that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. In simpler terms, the further a planet is from the Sun, the longer it takes to complete one orbit. And this relationship is predictable. Together, Galileo's telescope and Kepler's equations did something extraordinary. One gave people the vision to see a new universe. The other gave them the math to prove it. Copernicus had started the fire. Galileo fanned the flames. And Kepler built the framework that finally made it hold. After the door opened, it didn't take long before others walked through it and pushed even farther. The next generation moved to the next questions. Why do planets move at all? What force keeps them in orbit? Why don't they fly off into space or fall into the Sun? That's where the famous falling apple came in. Newton gave this invisible force a name: gravity. He realized that the same force that made apples fall from trees also held the moon in orbit, kept Earth circling the Sun, and ruled the dance of planets. He formulated it into a law: universal gravitation. According to him, every object with mass pulls on every other object, and the bigger the mass, the stronger the pull. The farther apart they are, the weaker the pull. Using Newton's law of universal gravitation, we knew that Earth orbits the Sun at about 7,000 kilometers. That's nearly 30 kilometers. Mercury moves even faster, around 47 kilometers, because it's closer to the Sun and feels a stronger gravitational pull. Mars, farther out, moves slower. Everything fits together. The closer a planet is to the Sun, the faster it has to move to stay in orbit. Newton's math proved it. He connected the motion of the heavens with the motion here on Earth. For the first time in history, we had one set of laws that applied to everything. And just like that, the great cosmic mystery of planetary motion, why they move, how fast they move, was no longer a mystery. It was gravity. But there was something else. Something no one expected. Because as scientists charted the heavens with better tools and sharper math, they noticed another motion, a bigger one, a deeper one. The Sun The thing we thought was at rest wasn't. It also was moving. But where? Chapter 2, Charting the Star's Path. After the Copernican revolution, the sun took the Earth's place as the center of everything. No longer did the cosmos revolve around us. Now it was the Earth that moved, spinning on its axis and orbiting the sun. This idea felt revolutionary, but once the paradigm shifted, the new model, the heliocentric one, began to settle. The sun, once seen as just another object in the sky, became our still point, the anchor of the universe, solid, motionless, and for a few hundred years, that idea held. But that would change, not with a physicist, not with a philosopher, but with a musician. William Herschel was born in Germany and moved to England as a composer. But he had an obsession: telescopes. He started building them in his spare time, grinding mirrors and designing optics better than almost anything else of his time. And when he pointed those telescopes toward the heavens, he didn't just look, he counted. Herschel became obsessed with structure. If the sky was filled with stars, were they scattered at random? Or was there a pattern? He decided to find out the hard way. He and his sister Caroline began a massive survey. He would count stars in narrow slices of the sky, just a few degrees wide, and note how many he could see in each direction. Over time, these counts painted a picture. He noticed something strange. Some directions had far more stars than others, and the highest density lined up with that faint band we call the Milky Way. So he made a map based on his star counts. He constructed what he thought was the shape of the universe, and it looked like a flat, stretched-out disk, like a grinding wheel with the sun roughly near the center. Today, we know he got the size wrong. He didn't account for interstellar dust, which blocked many distant stars from view. But for the late 1700s, this was extraordinary. He had figured out that the stars weren't infinite. They were part of a structure, a system, and we were inside it. He called it the galactic system. But Herschel didn't know it was a galaxy in the modern sense. He thought this system was the entire universe. He didn't realize that those fuzzy patches of light, those so-called nebulae, were actually other galaxies unimaginably far away. Still, what he did see was revolutionary. He showed that we weren't at the center of everything, not even close, and that flat shape, it meant something. It suggested structure, motion, orientation. If the Milky Way had a shape, then we had a location. If we had a location, then maybe we were also in motion. That's when people started asking a deeper question. Where are we really? And how can you tell what's moving and what's not? Because if everything is moving, how do you know when something is still? That's when we hit a wall. Not a wall of data, but a wall of perspective. Because everything we see from here, from Earth. Our eyes, our telescopes, our instruments, they're all sitting on this spinning rock that's itself orbiting the sun, which, as Herschel suspected, might be moving too. So how can you tell what's really moving and what's not? That's where a frame of reference comes in. Let's try a simple thought experiment. Imagine you're sitting in a train. You're sipping your coffee, reading a book. Out the window, you see another train next to yours. For a moment, it looks like that train is sliding backward. But then, wait, are you moving, or is it moving, or are you both moving? Here's the thing. Without seeing the ground, you can't know for sure. That's the trap of your frame of reference. From inside the train, everything feels still. The coffee stays in the cup. The book rests calmly on your lap. But to someone standing on the platform, you're flying by at 80 kilometers an hour. So who's right? Well, actually, both are, because motion isn't absolute. It's relative. And when your only window to the cosmos is from inside that moving train on a spinning Earth orbiting a star that's moving too, untangling what's really in motion becomes a puzzle. A puzzle that one man quietly and patiently set out to solve. Jacob's captain never saw himself as a revolutionary. He was quiet, careful, a man who loved numbers more than noise. But what he did with those numbers changed our understanding of the universe. Captain was born in the Netherlands in the mid-19th century. By then, Herschel's star maps were already over a century old. The idea that we were inside a star system, what we now call the Milky Way, was accepted. But the structure, the motion, that was still a blur. Telescopes were better, but astronomers didn't just need better tools. They needed a new approach. That's what Captain brought. He started collecting data, not just light, not just position, but proper motion, how stars shift across the sky over time. These were tiny changes, often fractions of an arc-second per year, but with the right math and enough time, they told a story. He gathered observations from observatories all over the world, the Cape in South Africa, Cordoba in Argentina, Sydney in Australia. Bit by bit, he compiled star catalogues, thousands of them, measured their brightness, measured their position, watched them drift, and then something strange showed up. The stars weren't just drifting randomly. They moved in patterns. Two general streams like cosmic currents seemed to flow across the sky. At first, it looked like the stars were grouped into two large rotating swarms, but Captain thought harder. What if this wasn't about the stars at all? What if we were the ones moving? Back to the train analogy. Imagine you're in the middle of a crowd, walking steadily through a busy plaza. People seem to be flowing past you in different directions, but maybe it is you who's in motion, and everything else only appears to drift because of your frame of reference. Captain then made the leap. He ran the calculations, and it all fit. The pattern of star motion only made sense if the sun was moving and dragging us along with it. This motion came to be known as the solar apex. According to Captain's results, the sun was headed toward a point in the constellation Hercules, at about 20 kilometres. Not a blazing sprint, but a steady, silent drift through space. And with that, the sun lost its stillness. The Captain didn't stop there. He wanted to go bigger. If we are moving through the stars, then what is this collection of stars? What is the shape of the system we're inside? Using the motion and brightness of stars, Captain began constructing what he believed was the true shape of our star system. He assumed stars were distributed evenly in space and that their brightness faded with distance. Based on that, he came up with a model. It looked like a flattened disc-like structure about 40,000 light-years in size. And in this structure, the Captain universe, the sun sat near the center. It was our first real attempt to map the Milky Way as a whole. Of course, we now know Captain's universe was too small. He didn't know about interstellar dust, microscopic particles floating between stars that absorb and scatter light, especially in the direction of the galactic plane. This dimmed faraway stars and made them look closer than they really were. So, his model underestimated both the size and shape of the galaxy. But for its time, it was groundbreaking. Then came a turning point. Astronomers began to wonder about those faint, blurry spots in the sky, the so-called spiral nebulae. Some believed they were part of our Milky Way, but others suspected something more dramatic, that these might be entire star systems of their own. That's where Edwin Hubble enters the picture. Using the Hooker telescope on Mount Wilson, then the most powerful telescope on Earth, Hubble focused on one of the most prominent of those nebulae, Andromeda. In 1923, he spotted something crucial inside it, a kind of star known as a Cepheid variable. These stars brighten and dim in a predictable pattern, and thanks to Henrietta Swan-Leavitt's earlier work, that pattern could be used to calculate how far away the star really was. The answer stunned him. Andromeda wasn't just far, it was way beyond the edge of the Milky Way. So far, in fact, that it couldn't possibly be part of our galaxy. This was a massive shift. For centuries, we thought the Milky Way was the entire universe. But now it was just one galaxy among many, a single island in a vast cosmic sea. But here's what really matters. By studying these other galaxies, we began to see our own more clearly. You can't look at the Milky Way from the outside we live inside it. It's like trying to map the shape of a forest from the base of a single tree. But with Andromeda and other galaxies, we finally had something to compare it to. We could look at galaxies from the outside and ask, does our galaxy have a spiral structure like that one? Does it have a central bulge, a flat disk, a halo of stars? Over the next decades, astronomers used this mirror effect, comparing external galaxies to what we could observe from within the Milky Way. They mapped gas clouds, star clusters, and the distribution of various stellar populations. They used radio astronomy to see through the dust that blocked our view in visible light. Gradually, a new picture emerged. One of them is a Dutch astronomer named Jan Oort, who took a closer look at the motion of stars near the Sun. He wasn't just interested in where stars were, but how they moved. And what he found was strange. If the Milky Way was rotating like a solid wheel, every star should be moving at the same angular speed, just like the spokes on a bicycle wheel. But they weren't. Some stars were lagging behind, some were moving faster. It looked more like a whirlpool than a wheel. Oort crunched the numbers and realized the galaxy rotates, but not evenly. It rotates faster near the center, slower at the edges. He worked out the math behind this and came up with two constants that described the way stars moved near our position in the galaxy. These constants, now called the Oort constants, gave the first real description of the Milky Way's differential rotation. From that, he calculated that our Sun is about 30,000 light-years from the galactic center and moving at an astonishing speed over 200 km/s. That's fast enough to circle the Earth 7 times in a single minute. At that speed, the Sun takes roughly 225 million years to make one full orbit around the center. That's one galactic year. And the Sun isn't alone. Every star you see in the sky is doing the same thing, spinning around the center of the galaxy like bees around a hive. We just don't feel it, because we're all moving together. But if that's the case, what exactly are we orbiting? To answer that, astronomers needed better eyes, ones that could see beyond visible light. So they turned to radio waves. Specifically, they began mapping out a faint natural radio signal given off by neutral hydrogen atoms. At a wavelength of 21 centimeters, this signal could pierce through the thick clouds of dust that made optical observations nearly impossible. By tracking this signal, astronomers began to map the spiral arms of the Milky Way from the inside. It was like trying to draw a picture of a forest while standing inside the woods. But now they had the tools to do it. And then came one of the biggest leaps forward, the Very Long Baseline Array, or VBA. The VBA isn't a single telescope. It's a system of 10 radio antennas spread across thousands of kilometers. Imagine placing 2 telescopes on opposite ends of the Earth, say one in Hawaii and one in the Virgin Islands. Now imagine syncing them so perfectly they act like one giant dish, the size of the entire continent. That's essentially what the VBA does. It links 10 radio telescopes scattered across the Western Hemisphere to form one super instrument capable of resolving incredibly small movements in the sky. And by small, we're talking about shifts so tiny they're measured in micro-arc seconds. That's like spotting a coin on the moon from Earth. They use this system to track cosmic beacons called masers. These aren't lasers you can see with your eyes. They're radio signals naturally emitted by gas clouds around newborn stars. These masers act like lighthouses in space, bright, compact, and perfect for tracking. Because they're locked to specific regions within our galaxy, they help us pinpoint both position and velocity. Over years of observation, astronomers watched these masers inch across the sky. They measured their change in position, that's proper motion, and also how their light shifted toward red or blue. That's radial velocity, whether it's coming toward us or moving away. Combine those, and you get a full 3D picture of motion. Not just left and right, not just forward and back, but the whole dance of stars across the Milky Way. And what did that dance reveal? It showed the stars orbiting the galactic center, but not in perfect circle. Their motion forms a spiral pattern, twisted and stretched by the pull of gravity and the structure of the galaxy itself. Some arms lead, others trail behind. The story starts ironically with the end of the universe, or at least with trying to predict it. In the 1990s, two teams of scientists, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were studying exploding stars called Type 1a supernovae. These explosions are incredibly bright, and they all explode in roughly the same way. That makes them perfect as cosmic mile markers. If you know how bright a supernova should be and it looks dimmer than expected, you know it's farther away. The goal was to measure the rate at which the universe was slowing down. You heard that right, slowing down, because the assumption at the time was that after the Big Bang, the universe started expanding and gravity, being attractive, was slowly pulling everything back. But that's not what the data showed. When they measured the supernova, something didn't add up. The galaxies weren't just far away, they were too far. The light was more redshifted than it should be, which meant the galaxies weren't just moving away, they were accelerating. The universe wasn't slowing down, it was speeding up. Now imagine being a physicist and suddenly realizing that every assumption about the future of the universe is wrong. That's what happened in 1998, and instead of brushing it off, the teams double-checked everything. But the results kept saying the same thing. Something invisible, something powerful is pushing the universe apart faster and faster. They called it dark energy. We don't know what dark energy is made of. We don't even know if it's a thing at all. But we do know it's real, and it dominates the universe. About 70% of everything out there, of all the energy and matter that exists, is dark energy. To understand how weird that is, think about this. Everything you've ever seen, touched, tasted, or heard in your entire life, all the stars, all the planets, every atom, makes up less than 5% of the universe. Another 25% is dark matter, which holds galaxies together with its gravity. And then the rest, the biggest slice of the cosmic pie, is this silent force pushing the universe apart. So what could it be? Here's where it gets tricky. Physicists have a few guesses. The most straightforward idea is that dark energy is just the vacuum energy of space. That even when space looks empty, it's not really empty. It's filled with quantum fluctuations, tiny random blips of energy popping in and out of existence. Now here's the interesting part. When you do the math, quantum theory actually predicts that empty space should have energy. That's not the crazy part. The crazy part is how much. The prediction is that the vacuum energy should be 10 to the power of 20 times stronger than what we actually observe. In other words, quantum theory overshoots the real value of dark energy by a factor so huge, it's the biggest mismatch between theory and observation in the history of physics. This is like trying to measure the weight of a feather and your calculator says it weighs more than the entire Earth. Yes, something's off. And here's the problem. This vacuum energy, the energy of empty space, isn't just sitting there quietly. According to Einstein's equations, energy and pressure shape the fabric of space-time, which means if space does have energy, then it affects how the universe expands. That's where dark energy comes in. We've observed that the universe is expanding faster and faster, so whatever is causing that acceleration has to be baked into the structure of space itself. And that's what led scientists to think maybe the vacuum energy is the thing driving this expansion. Maybe dark energy is just the energy of empty space. But if that's true, then quantum theory's prediction should match what we observe. And it absolutely doesn't. It's not just a little off, it's catastrophically off. So either something's wrong with our theory, or we're missing a huge piece of the puzzle. Now let's try to picture this. Imagine space as a giant loaf of raisin bread. Galaxies are like raisins baked into the dough. As the bread bakes, it expands and the raisins move away from each other. That's the universe expanding. But now imagine that halfway through baking, something turns up the heat way up. The dough doesn't just rise, it starts inflating faster and faster. That extra push, that's dark energy, and the bigger the bread gets, the faster it expands. Because dark energy isn't just sprinkled into space, it is space. The more space there is, the more dark energy there is. It's not diluted, it doesn't run out. That's what makes it so scary. So now we're standing here looking at a universe that's expanding faster and faster. And the engine behind that runaway growth, dark energy. This invisible, untouchable force that doesn't clump, doesn't slow down, and somehow gets stronger the more space there is. That's already weird. But now comes the truly unsettling part. Where does this take us? Let's say dark energy keeps doing what it's doing, keeps pushing, keeps stretching space. What happens in the long run? This leads us to one of the most terrifying predictions in all of cosmology. It's called the Big Rip. Here's how it works. In our current universe, gravity is still strong enough to hold things together. Galaxies don't get torn apart. Stars still orbit their centers. Planets cling to their suns. Even though space is expanding, the forces inside galaxies are still stronger than the pull of expansion in their neighborhood. But dark energy doesn't play by those rules. It grows. It's relentless. And in some models, it doesn't just keep accelerating the universe. It speeds up the acceleration. Like imagine you're in a car going faster and faster down a hill, and then the hill steepens. That's the Big Rip scenario. At first it's nothing you'd notice. Galaxy clusters would drift apart slowly. The space between the Milky Way and Andromeda would grow too fast for them to ever collide. But it wouldn't stop there. Eventually the galaxies themselves would begin to stretch, not just pulled apart, but ripped apart from the inside. Gravity would weaken. The bonds holding stars in place would falter. Then star systems like our solar system would come undone. Planets flung out of orbit. Moons lost to the void. The tides that held everything in balance gone. And it keeps going. As the acceleration intensifies, even the Earth itself wouldn't be safe. The force of expansion would grow, so strong it would overwhelm the electromagnetic forces that hold molecules together. The crust would crack. The atoms would break apart. Even protons, the building blocks of matter, could be torn as space itself stretches beyond what any particle can survive. In the final moments before the Big Rip, the universe would become a storm of disassembled pieces. 22 billion years from now there will be no galaxies, no stars, no atoms, just pure unbound energy flickering in a sea of nothing. That time is just a guess, based on one model. It could be sooner, could be never, because it all depends on how dark energy behaves, and that we still don't fully understand. But not every theory ends in shredding. Some go the other way. There's another idea, and it starts with a question. What if the expansion of the universe doesn't go on forever? What if at some point gravity fights back? You see, early in the universe, everything was hot and dense. Space was expanding, but gravity was pulling back, trying to slow everything down. That tug of war has been going on since the beginning, and for a long time, scientists thought gravity might eventually win. This is the theory of the Big Crunch. In this version of the story, expansion is temporary. One day, dark energy might weaken, or maybe it was never permanent to begin with. And if that happens, gravity could take control again. Slowly, at first, it would start to pull everything back together. The galaxies that once drifted apart would begin to close in. Structures would reverse. The great cosmic web would contract. Over billions of years, the universe would shrink. Temperatures would rise as everything gets squeezed into a tighter and tighter volume. The night sky would grow brighter, not from new light being born, but from old stars smashing together in a shrinking cosmos. The fabric of space-time would bend inward like a closing fist. In the final seconds, the entire universe would become a single hot, dense point, and then maybe it ends, or maybe it starts again. There's a poetic symmetry to the Big Crunch, the idea that the universe ends where it began, that the Big Bang was just one act in a cosmic cycle of expansion and collapse. Bang, then crunch, forever and ever. But there's a problem with this picture. The math doesn't quite line up. Everything we've observed so far, galactic redshifts, the cosmic microwave background, tells us the universe isn't slowing down, it's speeding up. That means gravity isn't winning, at least not yet. So unless dark energy changes dramatically in the future, the Big Crunch doesn't seem likely. But here's the thing, we don't fully understand what dark energy actually is right now. It's a placeholder term for something we can measure, but not explain. We know it's causing the universe to expand faster and faster, but we don't know why. If someone ever figures out the true nature of dark energy, it won't just be a breakthrough. It'll be Nobel Prize material. But until then, we're left with what we can see. Still, there's one more possibility, one more future. It's not as dramatic as a rip or a crack. It doesn't explode or collapse. It just keeps going, and that might be the most haunting ending of all. This is the Big Freeze, a universe that doesn't die in violence, but in silence. Here's how it happened. We've already talked about dark energy, how it drives the universe to expand faster and faster. We've also talked about how unless it changes drastically, that expansion is here to stay. Now imagine the universe continuing this path, galaxies drifting farther and farther apart, never slowing down, the stars inside them aging, burning through their fuel one by one. This idea, the cold endless fade, isn't just poetic. It's backed by some of the best data we have. Andrei Linde, a Russian-American physicist known for his work on inflation theory, has contributed to models that support this kind of ending. According to current cosmological parameters measured by tools like the Planck satellite and large-scale surveys like the Sloan Digital Sky Survey, the rate of expansion is consistent with a cosmological constant. That means dark energy likely stays the same over time, not increasing, not decreasing, just humming along, gently stretching space. If that holds true, then the Big Freeze isn't just a possibility. It's the most likely fate of our universe. Now let's zoom out and follow this future step by step. We're in the present day. Galaxies are still relatively close together. Stars are being born in places like the Orion Nebula. Planets are orbiting, life is breathing, black holes are eating, and the cosmic web is still glowing with energy. But time passes. A lot of time. Give it 100 billion years. By then the observable universe, what we can see, will shrink dramatically. Not because the universe itself is getting smaller, but because the space between us and distant galaxies is expanding faster than light can cross it. Those galaxies will slip beyond our cosmic horizon. We won't be able to see them anymore. They'll still exist, but forever out of reach, like ships sailing over the edge of an ocean that never ends. After enough time, even the nearest galaxies will vanish from view. Eventually the Milky Way and Andromeda, by then long since merged into one giant elliptical galaxy, will become a lonely island, floating in a dark, silent sea. Star formation won't last forever. Stars need gas, mainly hydrogen, to be born. But that gas doesn't last. As stars go supernova or shed their layers, they recycle material back into the galaxy. But over time, that recycling slows down. The fuel runs out. Estimates say that in about 1 trillion years, star formation across the universe will stop completely. The stars that are left, they'll burn through their fuel slowly. Red dwarfs, tiny, cool, dim stars, can last for trillions of years. They'll be the last beacons of light in an otherwise dark sky, but even they will eventually burn out. After that, only the remnants will remain: white dwarfs, neutron stars, black holes. Then we enter what's called the degenerate era. This is the time when there are no new stars, no new light. The universe is made of cold, collapsed objects, brown dwarfs and black holes still hungry, still devouring, and time just keeps going. Over the next 10 to the power of 40 years, that's a 1 followed by 40 zeros. These stellar remnants will decay. White dwarfs will cool until they become black dwarfs. Neutron stars might remain stable for a long while, but black holes, they have their own clock. According to Stephen Hawking, black holes aren't permanent. They slowly evaporate through something called Hawking radiation, a quantum effect that causes them to lose mass over time. It's incredibly slow. A black hole with the mass of our sun would take about 10 to the power of 67 years to completely vanish. Let that number sink in. Our entire universe right now is about 13.8 billion years old. That's nothing compared to the scale we're talking about. In the Big Freeze, time stretches far beyond what we can truly imagine. Eventually every black hole evaporates. One by one they disappear in tiny flashes of radiation. No more stars, no more planets, no more light. The universe becomes a place of particles, electrons, positrons, maybe some decaying protons floating alone in a sea of cold expanding space. Temperature drops toward absolute zero. Not because there's no heat, but because there's nothing left to generate it. No fusion, no gravity pulling things together. Just particles scattered across an ever-growing void. Even the protons might not last. If proton decay turns out to be real, then all matter itself could fall apart. Some models say that could happen in around 10 to the power of 36 years. So what's left? Nothing really. Just a whisper of radiation, a background glow from a universe that once burned with stars, galaxies, and life. A universe that expanded until everything was too far apart to interact. Too cold to change, even the concept of place becomes meaningless. The laws that gave birth to everything still remain, etched in a frozen, meaningless void. But there's no one left to read them, and that will be the ultimate fate of our universe.